Friends to the VLSI Problems and Solutions channel. Today we'll discuss metastability, setup, and the whole time. These are very important concepts in VLSI digital designs and extremely important interview topic. All VLSI interviews will touch this topic, so it is very important to thoroughly master these concepts. So the first fundamental question is, what is metastability? When setup or hold window is violated in a flip-flop, then the output signal attains an unpredictable value or state, which is known as the metastability. So in this slide, I'm showing a simple launch and a capture flop with some logic in between to explain the metastability problem that can arise. So these two flops get the clocks, and each flop has an output Q. So if let's say the launch flop Q starts oscillating, where its value is changing between 1 and 0 and it is not settling, the logic cloud will also be in an undeterministic state. So um, undeterministic state. So when the capture flop is trying to capture the value, it takes long, it has to wait for the oscillations to settle down. So that eats into the time available for logic to evaluate and produce a result. So that's the problem with the metastability, is it eats into your available time to capture the data launched by the launch flop. So in this slide, we'll discuss what are the best ways to avoid and fix setup time violations. So the first way, the fundamental idea behind solving setup violation is to make the data path logic quicker. If that doesn't work, then making the clock path logic slower will also help solve the timing problems. So let's go through these various options that we can use to solve setup time violation. Improve the setup time constraint of the capture flop. For any technology node, there will be several libraries that are provided by the fabrication vendor. These libraries have different processes, voltages, and temperature settings, and hence they all have different timing requirements. So the setup and the hold time requirements are different for different types of flops available in the library. When there is a setup violation on any path in the design, the capture flop can be replaced with a flop that has a smaller setup time window so that the path can accommodate large path delays. The next option is improve the drive strength of data path logic. The output capacitance of gate charges and discharges for the on and off operation of the transistor. Charging operation can be quicker if a flop with increased drive strength is used. This ultimately makes the data path logic quicker and hence eases the setup requirement on the capture flop. So the third point is reduce the clock to Q delay of the launch flop. Same as the setup time number, the clock to Q delay depends on the kind of the flop and on the library that is used. So different flops will have different clock to Q delays. Since setup time violation can be solved by decreasing the data path logic delay, using a flop with smaller clock to Q delay for launch flip-flop will ease the timing requirement. So the next option is using a faster cell for launch flip-flop. Flip-flop comes with various threshold voltages. Some flip-flops have less threshold voltage while some have higher threshold voltages. These flops are categorized as low VT, standard VT, and high VT. Using a low VT flop for launch flip-flop will result in less time for turning on and turning off of transistors inside the flip-flop that will ultimately result in faster data path logic. Other slow data path cells can also be substituted with faster counterparts to decrease the data path delay. Hence, substituting an low VT cell instead of standard VT or high VT can solve setup time violation. The fifth point is decrease the logic delay. Um, Another way to reduce logic delay, apart from replacing standard VT and the high VT cells with low VT, is to change the logic in register transfer level. This will most of the time result in increased latency, resources, and power consumption, but will ease timing requirement and solve setup time violation. The sixth point is reducing long routing wire. So in any ASIC, there will be different blocks scattered across the chip. For example, floor planning is done in such a way that memories are nearer to the power source near the pad and the processors are placed in the center of the chip. In place and route phase, care should be taken to avoid long wire connections between different flops from different blocks. Long wire increases logic delay, while a short direct connection will ease the timing requirement. The seventh point is increasing the clock latency on capture flop. Any toggling of net from launch flop should be sampled by the capture flop in the next active edge of the clock. It will ensure no data is lost. So setup time check will occur in the next active edge of the clock when the capture flop is sampling the change in the net. Because of uneven buffers and inverters in the clock path, there will be a difference in ideal clock position and actual clock position. This difference is referred to as skew. If there is more skew on the clock path to capture flop, then the setup time check is delayed until the clock reaches the capture flop. It will ease timing requirements and help solve setup time violation on certain path. So the last option is increasing the clock period. All the approaches discussed till now are optimizations that will be done in the chip development phase. When the chip is already taped out, these optimizations are impossible to be done. Under such circumstances, as a last resort, the operating frequency can be reduced by increasing the clock period. It will delay the setup time check and will give sufficient time for data to settle to a stable value before the setup check. The next topic is what are the best ways to avoid and fix hold time violations? So we have 8 different ways. We can discuss them one by one. The fundamental rule to solve hold time violation is to ensure slower data path logic than clock path logic. In other words, data should change after the active edge of the clock where the hold time check occurs. So the first method is improving the hold time constraint of launch flip-flop. As discussed previously, different types of flip-flops are available based on different library parameters. These flip-flops have different hold time requirements that needs to be fulfilled. Using a flop with less hold time requirement as launch flop will ease timing requirement and will help solve hold time violation when there is a large skew on launch flop. The next option is decrease the drive strength of data path logic. By decreasing the drive strength of cells found in the data path, we can slow the data path signals to capture flop. It's because the output gate capacitance will take a long time to charge and discharge. It will help solve the hold violations. Point number 3 is increase the clock to queue delay of launch flip-flop. Similar to the previous fix, by choosing a flop that has more clock to queue delay can be induced in the data path logic. It will ease timing and help solve hold time violations. Number 4 is use a slower cell for launch flip-flop. As discussed previously, there will be different corners of libraries available for implementation and they are typically grouped under low VT, standard VT, and high VT. By substituting low VT and standard VT launch flop with a high VT1, we can introduce delay in signal connected to capture flop. The higher threshold voltage will ensure delay to turn on and turn off compared to a low threshold or typical threshold. Point number 5 is increasing logic delay. Adding additional logic such as buffers can be to the data path logic to increase the delay on data path logic. It will make the data path slower than the clock path and will help with solving hold time violations. Number 6 is add long routing paths. Rerouting data path to make the connection long between the launch flop and the capture flop will increase wire delay, thus increasing the delay in data path logic. Next is reduce the clock latency on launch flip-flop. As discussed previously, skew plays a major role in the gap between the ideal clock edge and the actual clock edge. Increased skew on the launch flop gives the data less time to settle to a stable value before the active edge of the clock. Hence, keeping skew to a value as low as possible is necessary to reduce the number of hold time violations. And the last is reduce operating voltage. As after tape out, if there is a setup violation, it can be solved by reducing the operating frequency. The same cannot be done for the hold time violations, and hence at most precautions should be taken to avoid hold time violations. It's done by running simulations for worst case scenarios using fast corner libraries and higher threshold voltage. Despite all this, if a hold violation is discovered after tape out, it can sometimes be fixed by reducing the supply voltage. In conclusion, the metastability setup and the hold requirements are very critical in digital logic design. These topics are very essential to crack any VLSI interview. If you are a student or a professional, you will need to master these topics in order to succeed in your career. I have tons of experience and material which I'll be posting as time permits. Please subscribe to the channel VLSI Problems and Solutions to get the latest updates. Thank you.